excited to talk about how we are using a special type of AI called Physics-Informed Neural Network, or PINNs, to understand and solve problems in fluid dynamics. These are like smart tools that use both data and the laws of physics to predict how liquids move. The primary objective of this study is to explore the application of PINNs to solve the Reynolds average Navier-Stokes equations, or RANS equations, for incompressible turbulent flows by directly integrating the governing physical equations to the neural network architecture. This approach aims to reduce the resilience of empirical turbulence models and streamline the overall CFD simulation process. To start, let's talk about the Navier-Stokes equations. These are a set of equations used by scientists and engineering to predict how fluids flow. They take into account things like speed and pressure and viscosity, which is a measure of how thick a fluid is. We look at these equations in simple cases first, involving two-dimensional flows without compressing the fluid, which helps us build up to more complex situations. These techniques aren't just for academics. They have real-world applications. For instance, they can help in predicting and managing flows, designing efficient hydraulic structure, understanding how pollution spreads in air and water, looking at how sediments move in rivers, and even in medical scenarios like modeling blood flow in our bodies. Building on the basic Navier-Stokes equations, we then extend to what we call the RANS equations. These are special because they allow us to deal with the turbulent flows by averaging their effects over time, making the problem more manageable. The PNN setups include several layers: an input layer that takes simple X and Y hidden layers. Multiple hidden layers with nonlinear activation function are used to learn the complex relationship between inputs and outputs, guided by the governing equation. Output layer, the network outputs, the mean flow quantities such as velocities, pressure, and Reynolds stress, which are crucial for fluid dynamics simulations. And the last layer is a automatic differentiation. That is a technique which employed to compute the derivative of the outputs with respect to inputs, enabling the formulation of the Reynolds equation within the networks. To make sure our network is doing well, we train it using data and monitoring its performance through something called the loss function. The loss function is contained in the RANS equation. This helps us see how close networks prediction are to the actual data. We also use optimization algorithm to improve its accuracy over time. As you can see, the architecture of the model in this study was a fully connected neural network, deep fully connected neural network. Finally, we keep an eye on how the network learns over time, adjusting our methods if needed to ensure it's learning correctly. The result shows how effectively the network has learned to predict fluid dynamics, and we aim to see the error rates drop, indicating better performance. Also, the output of this study contain three type of contours. First of them is about the pressure distribution, and next two of them about velocity components. In first one, we can see model's ability to predict the fluid pressure. The result includes side-by-side comparison of the predicted pressure distribution against reference data. This visualization clearly shows that the model prediction align closely with expected outcomes with minimal errors, indicates high accuracy. Next, the model's performance in predicting two types of velocity is examined, similar to the pressure prediction that out in the comparative and error visualized. These results shows a satisfactory alignment with the reference data, particularly in crucial areas that demand precision. Finally, the overall accuracy of the model is quantified using the L2 norm error for each predicted variable, pressure and velocity components. This metric provides a clear numerical indication of the model's performance, with lower values representing more accurate predictions. The graphical representation of this error highlights that while the predictions for velocity are quite precise, the accuracy for pressure predictions shows room for improvement.